So our next presenter is going to show us how to write a reverb. And this is Geraint Luff, who is right down the street from me in Cambridge. And we've worked together quite a few times now. And he's a longtime DSP engineer and also the big boss at Signalsmith Audio. So he's CEO, CTO, and coding monkey. Is that how you described it?
Yeah, that's fair. Yeah.
So for people who are just getting started and want to learn how to write their first reverb, this is the presentation for you. So I will let you take it from here, Geraint.
Cool. Yeah, so I'll just share my screen so that you can all see what I'm about. Come on. There we are. Is that working?
Yes, it is.
Great.
And also, before you start talking, everyone on the chat who is following us, if you have a question for Geraint, please feel free to ask it on the YouTube chat, and we are going to ask them here live.
Yeah, and if I start not making sense, Timo, please interrupt me, because I don't want to talk for 25 minutes and then have to go back and
will do.
Turns out I've been talking nonsense. So yeah, hello. I'm Geraint. I'm Signalsmith on various forums and the audio programmer Discord. And as Josh said, I run Signalsmith Audio with my partner. We're developing some like audio plugin stuff, sort of VST3s, but we're also doing a lot of I guess freelance audio algorithm design and implementation, which is really good fun. And yeah, so today I'm here to talk about reverb. Reverb's one of my favorite effects, and particularly feedback delay networks are, I think, a great way to play around and try some weird things. And this presentation, there's not going to be code really. This is all sort of the design stuff, and we're going through one possible design which I think is very friendly, as in it's easy to configure correctly and get a good sound out of it. And it sort of sidesteps, I hope, some of the common reverb design problems which can give it a reputation of being tricky. But I think we can make something, and it's quite straightforward. So yeah, let's get to it. So first off, what is a reverb and what do we want it to do? So artificial reverberation is quite a wide field, and it covers a lot of different use cases. So we're going to take a pretty simple definition. A reverb creates a sense of space by generating a diffuse, long-lasting sound from a short input. Hopefully that makes sense. And there are a couple of ways to achieve this. One's convolution, and the other is, another common one is feedback delay networks. They both have their advantages and disadvantages. We're going to go the feedback delay route because you can get a decent sounding reverb with very low CPU and a pretty simple design. So here is a feedback loop. The input is sent through a delay, and then the delayed signal heads to the output, but it's also fed back into the delay input. So this means that the signal travels around in a loop, and it produces a series of echoes from a single input pulse. And there are a few variations on this, like where in the loop we take the output from, where the gain is, but this essential part, this feedback, which produces an infinitely looping series of echoes, and the gain is in here, which makes it decay over time. So now let's look at a multi-channel version of the same loop. Oh, sorry, I forgot to have audio examples. Yeah, here we've taken a pulse and we've just put it through the system, and you can hear it produces a very regular series of echoes. Yeah, so now this is a multi-channel version of the same loop. I could draw out, 4 parallel feedback loops. Here, I've just drawn double borders to say this is a multi-channel operation, and I've used colors. So yeah, the important thing to note here is that in this multi-channel feedback loop, each channel gets delayed by a different amount. So each channel produces a sort of independent echo pattern. Each channel is regular, but together they produce a slightly more chaotic and unpredictable result. So we can have a listen to that, and it goes like this. So it's slightly more irregular. That more complex sound is good for the kind of reverb that we want, because we don't want these regular juddering patterns. But in this loop that we have here, each channel only repeats its own echoes. So could we get an even more complex result if instead of just picking up their own echoes, each channel starts picking up echoes from the other channels? We can achieve this with a mixing matrix. This is an n by n orthogonal matrix, where n is the number of channels. A matrix being orthogonal, it means it preserves the input and output energy. So in this context, what it means is, as the signal goes around the loop, the energy can never go out of control. So being orthogonal means it's always kept in check. But as you can see, the more times it goes round, because there's this cross-pollination between the channels, the result starts getting more and more dense and chaotic. And so if we have a listen to that. So the tail end of that, if you just give that another go, it's starting to sound a little bit like a reverb, right? Hold on, because at this point, it's very tempting to mix the channels together as much as possible and put a bunch of other stuff inside the feedback loop to try and speed up diffusion. And there are some well-known designs like the Ring and Totoro's Figure of 8 and so on, which can be understood as instances of this feedback loop. And they work. They often require careful tuning, and as well as finding a good compromise for delay times. If you use too much inter-channel mixing, it can kind of lock the delays together, and that ends up not being good for the longer tail. In technical terms, if you have too much mixing, it moves the eigentones of your reverb closer together, and this leaves gaps which color the sound. But basically, designing a loop like this to produce a diffuse, long-lasting sound with no strong resonances in it is difficult. This is a hard problem. We don't have to do it. So there were two properties we said we wanted from our reverb. We wanted it diffuse and long-lasting. And even the basic feedback loop that we had earlier handles this long-lasting part quite nicely. The echoes carry on forever. They're not very dense, but they're there. So rather than trying to tune this feedback loop so it also produces a diffuse sound, in our design, we're going to separate the two concerns. So first, we take our input, and then we make a diffuse version of the input. And then we put that pre-diffused input into the feedback loop so that it echoes and reverberates and lasts. If this diffuser does its job well, we shouldn't need to build up echo density in the feedback loop. It can just repeat the sounds. Echo density is the number of echoes you have per second. And when you get between like 2,000 to 4,000 echoes per second, it starts to blend into this continuous diffuse sound that we want. So now we come to what I think is the big problem in algorithmic reverb design, which is you need a really good diffuser. So we want our diffuser to smudge the sound sort of in time without adding too much of its own timbre. And a useful concept here is the all-pass filter. All-pass filters have a flat frequency response. This means that whatever frequencies you put in the input, those same frequencies have the same energy in the output. The phase response gets messed up, which means some frequencies are delayed more than others, which is how the smudging happens. But what we have here is a Schroeder all-pass. This is a classic for sort of reverb diffusion basic tool. It's got a single channel feedback loop and an extra feed forward part, which gives it this flat frequency response. For the technically minded, here we can see impulse response at the top, And in blue, if you can see blue, there's that flat frequency response and this very wibbly phase response going on at the bottom. So for a reverb diffuser, the delay time in the middle here is typically, it's set to like a handful of milliseconds. So one all pass on its own doesn't provide much diffusion. You can put a bunch of them in a row, and the result is definitely diffuse. It does have a slight metallic edge to it, which is sort of the bane of these algorithmic reverb designs. So if you, all these audio examples, this presentation is going to be also in blog post form, so you can go back and listen to things and tell me if I'm lying to you. Yeah, so there's a slight metallic edge when you listen to this carefully. And if you actually want a kind of digital plate style reverb, this is a classic method to get it. You can make more sophisticated all passes if you replace the inner delay with another all pass. And you can make second order things and cascade them, and they improve the sound by creating a more irregular phase response. There are good designs here for diffusers, again, but choosing one of these designs or understanding why a particular all-pass structure is good, I don't find that very intuitive. It becomes another tricky tuning problem where you're choosing the delays and the feedback amounts, and then the all-pass structure itself, where you kind of stuff it inside itself and combine it in various ways. So I'm not actually very much a fan of these. Things get a bit more varied if we look at a multi-channel all-pass. So a multi-channel diffuser. First, we need to define what that actually means. So the idea of a flat frequency response, we have our input signal, output signal with the same energies in it. That's good. Let's phrase it slightly differently. So we'll say the total energy of the output must match the total energy of the input. So the sound comes in, but that sound might come out at a different time or in a different channel, but all the energy in the sound is preserved. The reason I'm talking about this is compared to the single channel case, we have a slightly wider range of basic building blocks available to us. So let's look at some examples. Much like, you could just have a single channel delay, you can have a multi-channel delay. And this is more interesting because the different channels can be delayed by different amounts. And specifically for our diffuser, if you have some echoes coming in to your multi-channel delay, then this can kind of desynchronize them so that the echoes are all at different times in the result. Another type of all pass, which only makes sense for the multi-channel case, is a mixing matrix. So we mentioned this briefly above, which is earlier. And yeah, so we treat each set of input samples as a vector. We apply this orthogonal energy preserving matrix, which is exactly what we need. And each output channel is a linear combination of the input channels. So this means that, if an echo only appears in one channel, this mixing matrix spreads it out amongst all the channels again. The Hadamard family of matrices, it's just a very good mixing amount. It does as much mixing as it's possible to do, and it can be done pretty efficiently. I'm going to link some example code for just a couple of useful bits like the Hadamard matrix on the blog post, so you can check that out and just copy it if you feel like it. And yeah, so just another thing we can do, it's not very interesting, but if you take your input channels and you swap them around, you just shuffle them, that's an all pass. What the energy coming in is the same as the energy coming out. And, you can invert the polarities on some of them. And there are loads more, right? There's a recursive all passes. So there's the Geraint, which is like a multi-channel version of the Schroeder that we saw earlier. You can apply the single channel ones to the individual channels or do things to some channels, not others. The thing I want to kind of emphasize here is that in the single channel case, when we're building a diffuser, these recursive IIR all passes are the only tool that we have. And you have to stuff them inside each other in complicated structures to get good results, basically. In the multi-channel case, we listed some basic building blocks, which none of them have feedback. They're all passes, but they're all finite, contained all passes. And from just the 3 examples that we mentioned, you can make a good diffuser, which is exactly what we're going to do. So here's the plan. We define a diffusion step, which is made from a sequence of multi-channel operations, a multi-channel delay, and then we shuffle some channels and invert some polarities. And these delays and the shuffling and the inversion can be just randomly picked. And then we put it through a mixing matrix. So from left to right, you can see we've got our multi-channel input. We do a multi-channel delay, so the different channels are now unaligned. And then after some shuffling, we put it through a mixing matrix. If an echo comes in, we unalign the echoes, and then the Hadamard matrix produces more echoes by spreading the new times across all the channels. So let's look at that animation again. Aligned, unaligned echoes, some shuffling, and then more echoes than we started with. So each time you put this multi-channel signal through a step like this, the number of echoes you have in it increases by a factor of n. So for here, it would be 4. For a larger number, like 8 channels, you can get a really dense diffuse result by putting a pretty small number of these diffusion steps together in a series. So let's listen to some examples. This is a 4-channel diffuser, as in the diagrams, and 3 diffusion steps. And each diffusion step is 60 milliseconds long. So the delays in the delay step are between 0 and 60 milliseconds. So, and it sounds like this. Again, it's a little rough. To get a smoother diffusion, you can add more steps, more diffusion steps, or increase the number of channels. Here's an 8-channel, 4-step diffuser. So, I mean, this is what happens when you put a click through it. You get this pretty good hiss, kind of burst of noise sound, which is kind of what you end up wanting for a reverb. You want it to turn a short sound into a diffuse sound. And yeah, you still need to choose the number of channels and diffusion steps, but by just repeating these diffusion steps, you can get a pretty good configuration and a good diffuse sound out of this pattern really easily. And there are obvious controls for just make this better, make it more diffuse. So a couple of things to note. We've created a multi-channel signal, and at some point you're going to have to mix this back down into a mono stereo output. The moment you do this mixing, it's not technically an all pass anymore. It's still a diffuser, and it's not actually a problem to kind of mix it back down, as long as there aren't any regular patterns in your phase response, because you'll hear those patterns when it's kind of collapsed back down. But this isn't a problem for us, because we're just going to be piping this multi-channel diffuse signal straight into our feedback loop. But I just felt I had to mention it.
Can I ask you a question right there? Yes.
Yeah.
So something that I was kind of a bit confused by at the very beginning, like, how do you split a signal into channels? Is it just, do you just copy them? Is it certain frequency bands, or what is it?
You can just duplicate it. So if you've got like 1 or 2 channels of input and you're operating with 10 channels or something internally, you can just repeat it 4 times. You could do left, right, mono stereo, left, right, mono stereo, or whatever it is. But honestly, this is a pretty robust design. So you take 1 channel and you somehow make 8 channels out of it. And then from there, use your diffusion. And the specifics of how you do that are actually not as important as you might think.
Thanks, that clarifies it. Yeah, thank you.
Great, cool. Thanks for asking. That means you're listening. Yes. I always worry that I talk too fast and everyone just nods their heads. He's off in one of his rants again. So another little detail that's just kind of worth mentioning. I said that the delay times in this, this diffusion step could be chosen randomly. That is one way to do it. Another neat trick, though, is if you divide your range that you want, say 40 milliseconds here, and you divide it up into equal segments, and then each channel's delay comes from a different segment, then your multi-channel delay ends up kind of equally, evenly distributed, but still random and not correlated enough to produce a identifiable timbre. This is similar if anyone's familiar with the velvet noise kind of reverb pattern. This is the same kind of logic, but this is for a multi-channel case instead of a single channel. And another thing, I've accidentally opened a link, there we are. Another thing to note is there's no reason that our diffusion steps have to be the same size. So you could have some shorter steps and some longer steps. To show the difference, we're going to do a really long diffuser. So this is an 8-channel diffuser, 5 steps as in the diagram, and they're all 300 milliseconds long. So this is a really long diffusion, if you can hear that. So that's from a click. That's our diffuser working pretty well. Here's the same setup, but with varying. So the first diffusion step's 48, then the next is 96, and they're all double the previous length. And it sounds like this instead. The difference is really subtle, and again, you might want to go through and listen to the audio examples on the blog post to make sure that I'm not lying to you, but basically it has a slightly faster attack, so it gets going more quickly, and less of a peak in the middle. But I mean, as I said, the small decisions like this, there's still stuff you can polish, icing on the cake, but fundamentally, both of these diffusers sound pretty good, and you can get a great sound out of this design almost whatever decisions you make, which is kind of the goal of what I was going for here. And yeah, that is kind of it. So we have our multi-channel diffuser, and then we have a multi-channel feedback loop, and all we have to do is put them together. So from left to right, we take our input, we can just duplicate it to get, say, 8 channels, and then we put it through a series of diffusion steps. So multi-channel delay, shuffle a bit, Hadamard matrix. Delay, shuffle, Hadamard. Delay, shuffle, Hadamard. We've now got a multi-channel diffuse sound. And then we put this straight into our feedback loop. You might notice that I've put a householder matrix. I have used a mixing matrix here. I would recommend householder because it's super cheap to compute, and it doesn't provide too much mixing, right? We don't want too much because the diffuser should be doing the diffusing. This is just making the sound carry on. Yeah. And again, at the end, you mix back down to mono or stereo. Just, however, have a go. Let's have a listen to see how this works. So we're going to use a pretty long configuration. So that's 8 channels, 4 diffusion steps, as in the picture here, with that doubling pattern that we mentioned. Pretty high feedback gain. So that's about 1.5 dB reduced each time it goes through the loop. And delays 100 to 200. And here's what happens when you put a little click through it. So I think that's a pretty smooth reverb sound from, hopefully, a design that makes sense, where you've got your diffusion, which is unaligning any echoes, and then respreading them, and then unaligning, and then spreading, and then unaligning and spreading to create this diffuse sound. Let's try it with some more musical inputs. So here is a bit of funky drumming. And then we put that through the reverb. I hope this is coming over on Zoom. Yeah, here's a bit of gentle piano. Ooh. Yeah, and then through the reverb. There's a slight resonance, but it's actually in the original recording, not the reverb. The reverb is resonance free. Yeah, so that's it. This is a pretty minimal reverb design, and there are a couple of ways that you might want to extend it. And I'm not going to do a massive deep dive into all the detail, but just sketch out a couple of things that you might want to add. So firstly, the delays in the feedback loop mean that you get some original sound that's probably coming through some dry path that we haven't put on the diagram. And these delays in the feedback loop mean that there's a gap before the first echoes appear in the wet reverb signal. To bridge this gap, you can pluck out the diffused signal from any stage and just do another little multi-tap that fills the gap between the first echoes that come through the feedback loop. So the earliest echo in the loop here, in our examples, was 100 milliseconds. So these could just be like a multi-channel delay between 0 and 100. And that gives you a nice, fills the sound straight away. Another thing that is really common in real spaces is that just tiny movements in the environment. So even like air currents, they produce subtle variations in the delay time of the space. And in feedback-based reverbs like this, we can model this by just gently modulating delay times. Or we can crank it way past realism and to get this supernaturally thick sound. There are a couple of places you might want to do this. You could modulate in the diffuser, and this will give you a kind of like a fixed amount of detuning, kind of like a chorus. Or you can modulate the delays in the feedback loop, and this means the detuning builds up and builds on itself over time, and that sounds really cool. It's worth noting that the moment you start modulating these delay times, you suddenly have to do fractional delays, which is a small amount of extra CPU. Any delay you're not modulating can and should be rounded to the nearest sample. And it doesn't matter if they're like aligned or whatever. We haven't made sure our delays are prime. We've just thrown a random number generator all this. Just don't worry about it. And one more thing which happens a lot in real spaces is high frequencies die away faster. Just most surfaces absorb high frequencies more. We can achieve this in a feedback-based reverb by putting filters in the feedback loop. So the gain here in the feedback loop is what determines how long the decay of the reverb lasts. So if you put a shelving filter in there, you can create frequency-dependent gain. So our example had 1.5 dB of decay every time it went around the loop. If we added a high shelf with another 1.5 reduction, then the high frequencies would die away twice as fast. And that gives a slightly more natural sound. Yeah, and I mean, that's just the basics, but from there you can add all sorts of weird things. These basic things are enough to get a really good sound. So here's just an example it's piano, a bit of synth bass, and then just the reverb. So it sounds like this. Yeah, so I think that's got a nice sound, smooth decay, good thick sound from the detuning. Yeah, that's it. Hopefully this wasn't too complicated, and hopefully that made sense. I really wanted to give this presentation because a lot of the feedback delay reverb designs that you see out there, they've got magic numbers in them, some of them, or you've got these all-pass structures that are kind of nested, and you're like, they feel like they've been very carefully tuned, and I don't think I could have come up with them. And it's not super obvious why they work. And I didn't like this at all. So one day, Josh asked me to write a reverb, with just no specifics, just, write a reverb. And I sketched out this design, which had no feedback or no IIR all passes. It's an FIR, a finite diffuser. And the design's robust enough that you can throw a random number generator, add all the delay times and the shuffling and so on, and it sounds good. It's a very robust design, I think, for making a reliably good reverb. This is a distilled version of that design, and I hope that this can be a useful starting point for people to just get going with reverb and then try a bunch of really weird things and then send them to me. I want to hear your weird sounds. Yeah, are there any questions?
Yes, there are quite a few, just a couple of questions here.
Great.
So Sudara is asking, they're interested to hear what types of algorithms you're excited about these days, like probably beyond reverbs as well. Or
Beyond
like
reverbs?
things, or maybe like,
yeah.
Like the things that you haven't talked about, but like anything you're excited about.
Well, non-linear stuff is always cool. Particularly at the moment, I've been working on some fun things that do frequency shifts, but not non-uniform. So it's not like shifting up, it's not shifting down, it's kind of just like making it a bit wrong. That's kind of fun. And I'm into, I've been writing a synthesizer, and there are some interesting like user interface problems where the answer, well, at least when I answer them, the answer has a lot of maths in it. Yeah, those are the kind of things I'm thinking about at the moment.
Cool, thank you. There's a question from Mike Boyenga. They're asking, do you have any rules or guidelines for picking delay times for the COM filters or any of the delays, shuffling, mixing in a diffuser?
Right. So in the diffuser, you can pick them randomly and it works. That thing where you divide it up into equal segments and then pick randomly from within that segment is, extra good. Try anything. It's good. Like there's no need to make things align. The delays in here, in the feedback loop bit, I think they're random. In the example, I've tried random. I've tried like exponentially distributed. It's all good because all the channels are like different versions of diffused signals. They tend to not interfere unless you've literally made them like all multiples of each other. So just random, try random, and then try exponential, and then give it a go.
So finally, there's one question by Wave Morpher. It's about the Soul reverb example. I'm not sure if you're familiar with Soul, but in case you are, it sounds like it might be using a similar algorithm to what you're using. Do you have any opinion on that?
I've no idea. That'd be cool. Okay. I've tried to find like a good description of this diffuser, where it's this delay and then Hadamard, where it's all finite and no recursion in the diffuser. If you've got something I can link to, so that I'm not just so it sounds like I know what I'm talking about, and I'm not the only person who's come up with a weird solution to this. Great, yeah, credit where credit's due if I'm not the first to do this, which I probably am not. Yeah, I haven't seen the reverb for the example for Soul, but sure.
All right, cool. And we have one more question actually from Phil Nock, who's asking, how do you compute the RT60 time for an algorithmic reverb like this?
Sure.
And also, can I ask another question on top of that? What is the RT60 time? Because I've not heard that term before.
RT60 is the number of seconds that a reverb takes to die away to 60 dB down from the original. So you clap or stick a pulse through it, and then if you wait 10 seconds, if that's your RT60, then it'll be Yeah, that's how much it'll die away. The way you calculate that is, say your RT60 that you want is 10 seconds. I think reverbs are often specified as RT20, which is the same thing for 20 dB. You say, how many times will the sound go through the loop in that time? So if your delay is 100 to 200 milliseconds, you might say, that's about 150. So divide 10 seconds by 150, that's how many loops you have in 10 seconds. And then you say, well, it's gone round, what that'd be, about 60 times. And I want it to die away 60 dB in 10 seconds. So I need to do 1 dB of decreasing by each round the loop. Does that make sense?
Yeah, that makes a lot of sense, actually.
Yeah, with the filtering that I mentioned to get the high damping, you can specify that decay rate for the low frequencies and the high frequencies separately, and then you just make sure that gain curve that you create with that filter matches that, and then you can craft your high and low decay times.
All right. I think Stein had a question as well. Are you still on the call here? Hello?
Yeah, I'm here.
Yeah, hi.
Well, not so much as a question, but for people that want to explore reverbs, Melda Productions has made a very nice domain-specific language to experiment with reverb algorithms in their M Turbo Reverb. Beside it being a nice plugin, they have also made a very nice YouTube series of how exactly all these L passes contribute to a proper diffuse tail and everything. So that those might be worth checking out. A very nice visual debugger too, so you can really see the quality of your tail, how it evolves if you change the algorithms.
Cool.
All right. And then we have one more question from the chat by Josep. How would you adjust the amount of diffusion in that design?
So you can increase or decrease the number of diffusion steps. So if you want more echo density, then you can just add more of them. So you pick some total amount of diffusion you want, say your echoes are, in this example, 100 to 200 milliseconds, you might want 100 milliseconds of diffusion. And you just kind of say, oh, well, I'm going to do that as a 25 and a 50 and then a 12 and a something, so the diffusion adds up and you add more stages for a denser one. And presumably fewer channels internally. You could use 4 instead of 8. 8's kind of what I'd recommend for like a solid result. Yeah, does that answer the question? Was that the question?
Yeah, I think it does, yes. Okay, well then I don't think we have more questions on the chat. So the only thing I wanted to add is thank you so much for this fantastic presentation. It was very clear, very engaging. Like I learned a lot. I wish everyone would just explain their DSP designs in such clarity. So I think really, really, really well done. Thank you so much. I think I learned a lot, and I hope everyone else out there did too. So yeah, definitely. Oh, actually, yeah, there's one question I have, I guess. You don't have a version of this somewhere like available open source or something like that, do you?
Not currently. I'm working on a version because I've created a version of this for a few different situations, but I was hoping to write one which is basically example code, so that I can, with this presentation, you can then see every step that I've made as code, but not currently.
But I think actually, if you are really into this kind of stuff and you want to learn, you could go in and code it yourself. And I think you kind of outlined it to a sufficient detail that I think people could actually play around with that stuff. So
that's the dream. Yeah.
Yeah, that's really cool. Well, I don't see any more questions on the chat. So yeah, thank you so much. And yeah, I'll give the mic back to Josh.
Yeah, thank you so much, Geraint. This is so many people are giving their positive feedback about your presentation, and this is really awesome. And thank you once again, Stein and Priscilla. This is really fun. This is a lot of fun, and I really appreciate you sharing your